Today we're starting the topic of organic chemistry, and organic chemistry is the study of substances that contain carbon. Carbon is a group 14 element. If you take a look at your periodic table, if you look at this guy right here, this represents carbon. Carbon has these 4 valence electrons. Okay, compounds that contain carbon are considered organic. You know that it has 4 valence electrons, so what would that mean that it needs? How many more electrons does it need to fulfill the octet? If you take a look at this Bohr model of the atom, I'm showing you how there are 2 electrons in the inner level and 4 on the outside. There's the 4 valence. In order to fill the octet, we would need to have 4 more valence electrons. So for this reason, carbon does tend to bond covalently, which means it's going to form connections sharing its electrons with other non-metals. It could sometimes form these gigantic chains. In this particular ring, there would be several carbons in here, and they're going to form connections so that they can get to the octet. Covalently bonded structures we know are called molecules, and they tend to be nonpolar. That has to do with SNAP. If you remember SNAP, nonpolar means it is symmetrical. And remember that idea that like dissolves like, so we need to find other symmetrical molecules if we wanted to dissolve an organic structure. They tend to have a low melting or boiling point, which should flag you as thinking about that it must be weak. These are weak bonds if they have low melting and boiling point. They're poor conductors, which make a ton of sense because they do not have any metal in them. And they are non-electrolytes, which means they do not conduct electricity when you put them in water. The types of bonds we might see for organic molecules, the first one is saturated. If you're looking for a saturated bond, that would be when all the carbon-carbon connections are single bond only. So you're looking for single bonds between only the carbon-carbon connections. If you had an unsaturated organic substance, there'd be at least one double or one triple bond. It could be more than one double, it could be more than one triple. There could be several single bonds. If you see a double or triple bond in there, it must be unsaturated. How many electrons would be shared in a double bond? If you take a look right here, this double bond in the molecule represents 2 electrons in one line, 2 electrons in the other. So a double bond would have 4 total electrons being shared, and a triple bond would have 6. This next slide, I just put all at once. It was coming up in a funny way. But you recall that we've talked about these different types of formulas. An empirical formula is the lowest ratio, which means we could reduce the values of the subscripts down as low as they could possibly go. A molecular formula would be the actual true formula. And a structural formula would show how we would depict it if we were to see it in real life. So if you take a look at that side picture, you could see that CH4, which happens to be methane, this is an empirical formula. I cannot reduce it anymore. It is also the molecular formula, the true formula for methane. And if we were to draw it, it would look like the structure to the side. If you take a look at something like butane, butane C4H10, that is the true molecular formula. If I reduced it to empirical, it would be C2H5, and the structural formula, true structural formula, is to the right of that. Now, if you take a look at the very bottom, it says homologous series table Q. I want to just get a look at table Q with you for a moment. On table Q, we're going to be looking at hydrocarbons. Hydrocarbons contain only hydrogen and carbon. And we're looking at table Q, we could see that these are called alkanes, alkenes, and alkynes. These are 3 types of hydrocarbons that we'll be looking at. The homologous series just means they're related. So when you see the word homologous, don't panic. It's just table Q. And if you take a look at these general formulas here, you could see how these general formulas represent the alkane series. So every alkane will have this formula where that N could be a number of carbons. So if you look, ethane happens to be 2 carbons. CN would be C2. Then take that 2 and plug it in here. H2 times 2 is 4, plus 2 is 6. That would give me the formula for ethane, which happens to be C2H6. And the structural formula is right there shown for you. Okay, this is the last slide, and I just wanted to give you an idea of how the homologous series of hydrocarbons, specifically for those alkanes would change. As you change the number of carbons, you could see how the number of carbons changes the structure, just a straight line chain, adding 1 carbon each time, but adding more hydrogens. If you take a look, these are all considered saturated hydrocarbons because all the carbon-carbon bonds are single bonds. So these are all saturated. The saturated hydrocarbons are the alkanes. So all the alkanes are considered saturated hydrocarbons. And one quick last thing, if you took a look at something like methane at the top versus decane at the bottom, just by looking at the size of it, hopefully you might think about boiling point and melting point. Even though these are weak and they do have low melting point and boiling points, the more carbons you have, the higher the melting and boiling point. So even though they are weak and low melting and boiling points, methane definitely has a lower melting and boiling point than something like decane.